All right, last piece for sequences and series. This one's all of this thing called infinite geometric series. So the first thing we're going to do is define infinite geometric series. Then we're going to differentiate between converging and diverging series. Then we're going to evaluate infinite geometric series. And then the last one doesn't seem to fit, but I'll show you how it's related. It says convert repeating decimals to fractions. Let's start with the warm-up. Let me read these through, and then I'd like you to pause the video and then try these on your own. So it says, write the first 5 terms of each sequence. The first one goes a sub 1 equals 4, and a sub n equals 3 times a sub n minus 1 minus 2. The second one just says a sub n equals 2 times n squared minus 7. First one, well, actually, I'd like you to pause the video. And now let's continue as if you all had paused. A sub 1, to find the first term. On that one, you're given the first term. I already did 20% of the work for you. You are welcome. A sub 2. We got 3 times this part right here. Remember, a sub n minus 1 really means the previous term. So to find the second term, we got to do 3 times the first term, then minus 2. So we have 3 times 4, which is 12, minus 2 gives us 10. To find our third term, we're going to repeat that same process. 3 times the previous term, 10, which is 30, minus 2 gives us 28. To find the fourth term, a sub 4, we're going to do 3 times the previous term, so 3 times 28, minus 2. 3 times 28 is 84, minus 2 gives us 82. And then a sub 5 gives us 3 times 82. That's 246, minus 2 gives us 244. So the first 5 terms in order, we got 4, 10, 28, 82, 244. Now that was a recursive formula because we had to keep referring back to previous information. This next one, a sub n equals 2 times n squared minus 7, that's an explicit formula. We don't need to know any previous terms to find whatever term we want to find. So we could, if we wanted to, find the 50th term just by plugging in 50. Well, we don't need to do that. We just need to find the first 5 terms. So we got a sub 1 equals 2 times 1 squared minus 7. 1 squared, doing that order of operations, the exponent's got to come first. 1 squared is 1, times 2 is 2, minus 7 is negative 5. A sub 2, we're going to, instead of plugging in 1, we're going to plug in 2. So we got 2 times 2 squared. So 2 squared is 4, times 2 is 8, minus 7 gives us 1. A sub 3 equals 2 times 3 squared minus 7. So we got to do the 3 squared first, which is 9 times 2, which is 18, minus 7 gives us 11. A sub 4, we got 2 times 4 squared minus 7. 4 squared is 16, times 2 is 32, minus 7 gives us 25. And finally, a sub 5 equals 2 times 5 squared minus 7. 5 squared is 25, times 2 is 50, minus 7 is 43. So the first 5 terms of that sequence, negative 5, 1, 11, 25, and 43. Just a bit of a refresher from some of the formulas we've done in the past. All right, let's talk about this new thing called infinite geometric series. We've talked about geometric series in the previous lesson, where you're just multiplying by one or by the same value to get from one term to the next over and over and over and over. An infinite geometric series is related. It's got the same type of pattern, but it's got an infinite number of terms. So it has an infinite number of terms, and we're going to be adding those together. So say, for example, you've got a pattern here that goes 3 plus 6 plus 12 plus 24 plus, and it's going to keep on going. We're going to use those points of ellipse to imply that it keeps going forever and ever and ever. So this is one that has a ratio of 2. You're multiplying by 2 every time. You could also have one that's maybe 1/2, 1/8. Oops, sorry, not commas there. It should be pluses there. So 1/2 plus 1/8 plus 1/32 plus 1 over 128 plus ... and that keeps on going forever and ever as well. And we're going to say r equals 1/4. Now, adding up an infinite number of terms seems impossible. Like if you do 3 plus 6, that's 9, plus 12 is 21, plus 24 is 45, plus 48. It's going to keep on getting bigger and bigger and bigger and bigger and bigger. Well, so's the other one. 1/2 plus 1/8 plus 1/32. Like, those are small numbers, but it is going to keep on getting bigger and bigger. Sometimes we can say that they have an infinite sum. Sometimes we say they don't. We'll talk more about that in a little bit. So the two types that we're talking about, one we're going to call it convergent, the other one we're going to call it divergent. An example of a convergent series, well, I'm getting a little bit ahead of myself, sorry. Looking at these two patterns, we got 1/2, 1/4, plus 1/8, plus 1/16, plus 1/32. To get from one term to the next, we're multiplying by 1/2 over and over and over. Now the second one uses the exact same fractions in a different order. It goes 1/32, plus 1/16, plus 1/8, plus 1/4, plus 1/2. The R value there is 2. Even though we're using the exact same values, the order that they are in makes a huge difference, what we're multiplying by every time. And this is what I was getting ahead of myself a minute ago, talking about these things called convergent and divergent. A series diverges if the absolute value of R is greater than 1. And I'm just going to say terms get bigger. And remember, I'm using the word bigger in terms of absolute size. So for example, -1 million is bigger than +10. It's less than, but it's bigger than. A series converges if the R value, or the absolute value of the R value, is between 0 and 1. And for that one, I'm going to say the terms get smaller. So it diverges when terms get bigger, converges when terms get smaller. Let's take a look at example 1, quickly see if we can identify whether the terms are getting bigger or smaller, and whether that means it converges or diverges. So on this first one, letter A, it says 10 plus 1 plus 0.1 plus 0.01. The R value there, what are we multiplying by every time to get from one term to the next? Well, some of you might look at this and say, oh, that's dividing by 10, dividing by 10, dividing by 10, and that would be 100% correct. But remember, when we're describing our ratios, we're talking about what we're multiplying by. Dividing by 10 is the same thing as multiplying by 1/10. So we always want to put it in terms of what we're multiplying by. So R equals 1/10. If it helps you to think about it as a decimal, it's 0.1. And that is between 0 and 1, so we're going to say it converges. I'd like you to pause the video for a second, see if you can figure out the pattern going from one term to the next, to the next, to the next for B and C, determine whether you think it converges or diverges. And I'm going to jump right back to it, pretending that you guys all paused, pretending you tried these two on your own. If you did, great. If you didn't, also great. I don't really know. Take a look at letter B. To figure out our ratio here, the easiest way to figure out the ratio is to go take one term. I'm going to take the second term, divided by the previous term. 1 divided by 2/3. Dividing by fractions. Yuck. Let's see if we can change that up. We got 1 times multiplied by its reciprocal, 3/2. So it's 3/2 or 1.5. We're multiplying by 1.5 every time. So again, our R value is 1.5, or if you prefer it as a fraction, which I do, 3/2. That is bigger than 1, so that is going to diverge. Letter C, taking a look at the pattern there, this one I think is a little easier to see. That's multiplied by 3, multiplied by 3. Guess what that one is? That's also multiplied by 3. So our R value is 3, so that one also diverges. The terms are getting bigger and bigger and bigger and bigger.